Hello everyone. So we were just studying the scale analysis for the low Prandtl number and the high Prandtl number, and we derived the for high Prandtl number. If you just took the slides from the high Prandtl number, you had taken the delta t as h RAH to the power of minus 1 by 4, Nusselt number as RAH to the power of 1 by 4. We got the velocity as a function of alpha by h and RAH to the power of 1 by 2. And we realized that delta by delta t is of the order of Prandtl to the power of half. That is, delta is indeed greater than delta t, which is apparent from this figure as well. So now if we consider low Prandtl number, which is given in this figure, and the low Prandtl number also we had worked out delta t, Nusselt number and v, and we summarized all these scales. We summarized all these scales here for thermal boundary layer thickness, distance from the wall to the velocity peak, thickness of the wall jet, velocity scale, Nusselt number. We summarized for Prandtl number greater than 1 and less than 1. We can see that for Prandtl number greater than 1, except delta, for all parameters, it is function of Rayleigh number alone. But for Prandtl number less than 1, for every parameter, delta t, delta v and Nusselt number, they are dependent not just Rayleigh number but also Prandtl number. So that is the difference between Prandtl number greater than 1 and Prandtl number less than 1. That's the reason why we summarized that. And the non-dimensional numbers which we introduced ourselves is the Grashof number g beta delta t h cube by nu squared, Reynolds number u infinity h by nu, Rayleigh number g beta t minus t infinity h cube by alpha nu, Prandtl number nu by alpha, Rayleigh number equal to Grashof into Prandtl. Here u infinity, what we have taken, cannot be u infinity, can be visualized as something as like our v here. What we have gotten v can be taken as my u infinity, although I am taking it as, because v is the one which is generated by virtue of the buoyancy force, that is Rayleigh number. So now we said that we will do similarity approach. Let's get started with similarity approach. Similarity approach. So in the similarity approach, we write our equations as del u by, we are writing boundary layer equations only, del u by del x plus del v by del y equal to 0, u del v by del x plus v del v by del y equal to nu del squared v by del x squared plus g beta t minus t infinity upon here u del t by energy equation u del t by del x plus v del t by del y. You can write alpha del squared t by del x squared. The other term will be negligibly small. So you non-dimensionalize x star equal to x by L and y star equal to y by L and u star equal to u by u infinity and v star equal to v by u infinity and t star equal to t minus t infinity upon ts minus t infinity. So if you non-dimensionalize the continuity equation, you just get del u star by del x star plus del v star by del y star equal to 0, nothing new, nothing important from continuity equation. So if you take the momentum equation, so you get, if you use, you can write for u, u infinity into u star, for v, u infinity squared by x, so u infinity squared by h, sorry, this is h, I have to non-dimensionalize this with h. So if we, so u infinity squared by h into u star del v star by del x star plus v star del v star by del y star, because you have velocities, two velocities and one length scale, and every velocity I am non-dimensionalizing with u infinity and every length scale I am non-dimensionalizing with h. So the common should be u infinity squared by h is equal to nu, v becomes now u infinity, that is del squared v star upon del x star squared. X star squared is nothing but h squared. Okay, students usually get confused, so I keep asking them what is the unit. So they they simply say meters per second. So I have to correct it. This is meters per second upon meter squared. That is the unit of this del squared V upon del x squared. So that you get nu u infinity by h squared, this is the term, plus g beta. Now if you write t equal to t star into ts minus t infinity plus t infinity. So if you differentiate this, or write for, in this case this differentiation will come later on, here for t minus t infinity I can write g beta into ts minus t infinity into t star. So let me make this multiply by h by u infinity squared. So nothing, no coefficient is there on the left hand side. So I get u star del v star upon del x star plus v star del v star upon del y star is equal to nu u infinity by h squared into h by u infinity squared, because that's what I am multiplying with, into del squared v star upon del x star squared plus g beta ts minus t infinity into h by u infinity squared into t star. Okay, so let's write this again, because we need to get these coefficients in the non-dimensional form. That's our aim. So you get u star, left hand side remains same, del v star upon del x star plus v star del v star by del y star is equal to nu by u infinity h, that's what you get, into del squared v star upon del x star squared. So here I need to do some readjustment. G beta delta t, that is ts minus t infinity into h, let me multiply by, that is h squared, h cube divided by nu squared. So I have taken nu squared here, so I have to multiply by nu squared by, I have multiplied by h cube, so I have to divide by h cube, so I have h here already, and u infinity square. Okay, so this is the readjustment. So u into t star. Now what is this? Nu by u infinity h is nothing but 1 by REH. Now whole of this is nothing but my Grashof number, GRH equal to G beta Ts minus T infinity into h cube divided by nu square. Now what about this? This term is nothing but nu squared by h squared u infinity squared, that is 1 by REH squared. So I get my equation as u star del v star by del x star plus v star del v star by del y star is equal to 1 upon REH into del squared v star upon del x star squared plus GRH upon REH squared into T star. So these are the non-dimensional numbers which I get from momentum equation. This is my momentum equation non-dimensionalization. Let me take the energy equation. The energy equation is U del T by del X plus V del T by del Y equal to alpha del square T by del X square. Now T star equal to T minus T infinity upon Ts minus T infinity. So T equal to T star into Ts minus T infinity plus T infinity. So if you take del t by del x, you get del t star by del x, and Ts minus T infinity is constant. Okay, and similarly del squared t by del x squared, you get del squared t star upon del x squared into Ts minus T infinity. So if you put this, so you get u star, that is before getting u star you get u infinity into Ts minus T infinity upon x is h. So you get u star del t star by del x star plus v star del t star by del y star is equal to alpha into Ts minus T infinity upon h squared, Ts minus T infinity upon h squared into del squared T star upon del x star squared. So now if I just take, if I divide throughout by u infinity Ts minus T infinity by h, so I get u star del T star by del x star plus v star del t star by del y star is equal to alpha into Ts minus T infinity by h squared into h upon u infinity into Ts minus T infinity into del squared T star by del x star squared. Okay, so now what do I get from this? This Ts minus T infinity gets cancelled out. So I get alpha by u infinity h. So what do I do is alpha by nu into nu upon u infinity h. I have multiplied and divided by nu. So nu by alpha is Prandtl number and u infinity h by nu is REH. So I get my energy equation as u star del t star by del x star plus v star del t star by del y star is equal to 1 upon REH into PR into del squared t star upon del x star squared. So the non-dimensional numbers what we have come across are RE, Reynolds number, and the most important grouping of the buoyancy force which you have non-dimensionalized is GRH by RE squared, which is having a lot of significance. I will explain you just a little while from now, and then REH into PR. So now if we consider, so before we consider GRH by PR, now I want you to notice, let us rewrite the equations once again. So because there is a reason, let's write the equations once. Del u by del x plus del v by del y equal to 0, u del v by del x plus v del v by del y equal to nu del squared v by del x squared plus g beta into t minus t infinity and u del t by del x plus v del t by del y equal to alpha del squared t by del x squared. See, please notice, we could solve in the forced convection mass and momentum together and then take that velocity distribution and put it in energy equation and solve the energy equation. But now that's not the case. T is in the momentum equation itself. That means these equations are coupled. So you need to solve them simultaneously. In order to get u, v, t, which will fetch me delta t nu. So that is what we got, that is u star v star t star is a function of REH, Prandtl number, Rayleigh number. As you have already seen, our Nusselt number was function of Rayleigh number and Prandtl number. Okay, so that's how we can understand. The main thing I want to emphasize here is that in the natural convection, the equations are coupled. Unlike the forced convection, where one can solve mass and momentum and then take up the energy, here you have to take all three together. That makes little math cumbersome. But now let us understand what is this physical significance of GR by GRH by REH squared means. If GRH by REH squared is less than 1, very much less than 1, that means what? Grashof number is less than Reynolds number. That implies, because in the real life both forced convection and natural convection would be there, which one is dominating is the question most of the times. So forced convection we can say is dominating when Grashof number by RE squared is very much less than 1, and GRH by REH squared, if it is greater than 1, naturally it would imply that it is natural convection. And if GRH by REH square are of the order of 1, then it implies both natural and forced are important. Here forced convection dominates, natural convection dominates. Okay. So now let's come to this slide where I have plotted Nusselt by REH to the power of half upon Grashof upon REH squared. Please note this is a logarithmic plot, both these sides. So you can see that actually what does this represent? This horizontal line represents pure forced convection, because GR by REH squared is less than 1. So this is forced convection. But if GR by REH is greater than 1, this is the solution of pure free convection. This is the correlation used for Nusselt number based for forced, and this is for free. But you see that, you can see that, you see here the knee for Prandtl number 0.72 is around 0.4, knee for 10 is around 0.5, and knee for 100 is 1. So the transition from forced to free depends on the Prandtl number, not just the Grashof and Reynolds number. This we need to realize. So generally people say that, although we cannot conclude because it depends on the Prandtl number, generally we can say that if GR by RE squared is less than 0.1, forced convection. If GR by RE squared is greater than 10, definitely forced convection, because here from the figure we can say that. And less than 0.1, no matter what is the Prandtl number, you can say that it is indeed forced convection. And in between these two, we say that natural and forced convection dominates. But I would say that it's better to go with this plot for a particular Prandtl number and decide your range accordingly, rather than making the generalizations. So much about the criterion. Now, if we have to really see what is the actual result we get for Nusselt number, because we just got Nusselt number, if you recollect, for Prandtl number greater than 1, we got that Nusselt number, that is HH by K, is of the order of Rayleigh number to the power of 1 by 4 we had gotten. So we can write that this is equal to C into Rayleigh number to the power of 1 by 4 for Prandtl number greater than 1. So what is the C comes from the closed form solutions or the experiments. Remember these properties for the Rayleigh number, that is Rayleigh number equal to G beta Ts minus T infinity H cube upon alpha nu. These properties are calculated at mean film temperature. That is Tf equal to Ts plus T infinity by 2. This is very important because all the fluid properties are very sensitive to temperature. So if you take either Ts or T infinity, we will be making a mistake. So it works well with the experimental comparisons only when you take the mean film temperature. So if we come to these slides, if you just see the slides, for a vertical plate, here my intent is not to give all the correlations. I will just give for vertical plate, horizontal plate and inclined plate, and for maybe circular and spherical, but various other shapes, any standard textbooks one refers, you will get the correlations. So I would strongly recommend you to either see Incropera and Dewitt or Bejan or Changal for getting those correlations. So here if you just see the vertical plate, here there is one correlation for a vertical plate for Rayleigh number between 10 to the power of 4 to 10 to the power of 9, Nusselt number is equal to 0.59 Rayleigh to the power of 1 by 4, and for Rayleigh number is equal to 10 to the power of 9 to 10 to the power of 13, Nusselt number is equal to 0.1 Rayleigh number to the power of 1 by 3. What is the difference between these two? The top one for the low Rayleigh numbers, that is between 10 to the power of 2 to 10 to the power of 9, the boundary layer is laminar, and beyond 10 to the power of 9 it is turbulent. This we have not derived, I am just giving. You can say that it has come from experiments. Of course, you can analytically also derive that, but I am not teaching that. So this is Nusselt number equal to 0.1. You can see that although the coefficient is less, here the power is high, because of which you are going to get higher number, Nusselt number for turbulent compared to that of the laminar flow. So combined equation, there is another equation if you see the slides, that is 0.825 Rayleigh number to the power of 1 by 6. It works for the entire range. It's little complex, but I think everyone uses this equation because it works well and it is more accurate. And if it is a inclined plate, all that you need to do is, in the Rayleigh number, instead of G, you need to replace G with G cos theta, where theta is, if this is your plate and this is the theta with respect to the vertical. So this is what is the theta for inclined plate. If my plate is inclined, this is for inclined plate. The same correlation holds good, except for the fact that you replace G with G cos theta for Rayleigh numbers less than 10 to the power of 9. Okay. So if you come to the horizontal plate, if you see the horizontal plate, the Nusselt number for the horizontal plate, that is heated upwards, the bottom is insulated. So you can see that the Nusselt number equal to 0.54 Rayleigh number to the power of 1 by 4 for 10 to the power of 4 to 10 to the power of 7. You see, whether it is vertical or horizontal, the value is almost same. Okay, it's not very much different. So generally we think that only the vertical plate, the natural convection is higher. So this is what you get for horizontal plate. But if your horizontal plate is insulated on the top and heated bottom, so the natural convection current will form like this and go up. So it is not very easy for the fluid to move up. So you can expect the lower Nusselt number. So the Nusselt number for this situation is 0.27 Rayleigh number to the power of 1 by 4. It's almost half. It's almost half. And this is valid for 10 to the power of 5 to 10 to the power of 11. So this is the correlation. So if you come to the cylinder, so you have a vertical cylinder which can be treated as a vertical plate for diameters greater than 35 L upon Grashof number. You can just use the same correlation for just by taking the length of the cylinder, so that the curvature effect is neglected. So horizontal cylinder, this is the correlation for Rayleigh numbers based on diameter. So instead of H, you have to replace in the Rayleigh number D, that is G beta delta T. Instead of H cube, it will be D cube divided by alpha nu. So that is this correlation you will use. And for Rayleigh number, these are all for constant temperature boundary condition. This is for sphere. This is for sphere, and you have correlation which looks similar to that of the cylinder, only the coefficients are a little different. But all these correlations are for constant wall temperature. At the end of this 2-3 modules, I am going to tell you what is that which is going to be for the constant heat flux boundary condition. So with this, we are going to, in the next module, I am going to take up this problem of a horizontal cylinder water pipe and what are the natural convection. And most of the times what happens is, in the natural convection, this problem is going to tell us that in natural convection, radiation is also as important as natural convection. In forced convection, you generally can perhaps neglect radiation, but in natural convection, you cannot neglect radiation. Almost it is 50-50 in this horizontal cylinder problem. In the next module, I am going to make you appreciate that this radiation cannot be neglected in the natural convection situations. Thank you.